So let's start off this particular lecture with one of these check your neighbor questions. And the question is if you were to go to the hardware store and buy a pipe, then you need to supply the water that you want to go through this. However, if you were to go to the hardware store and buy a copper wire, the electrons that are going to do the flowing, for lack of a better word, are actually already in the wire. Essentially what's going to happen is here I'm going to have my wire. It's made up of some material, copper. And it turns out that copper is going to have some free electrons, just like all metals will. And those electrons are going to be the things that do the sloshing back and forth. So now let's go ahead and keep on talking about the attractive or repulsive nature of charged particles. However, of course, this is a physics class. I've got to go ahead and give you an equation for it. I've said that if we had two opposite charges, they're going to attract, and if we had two like charges, that they're going to repel. So we know these guys are going to repel each other. We know that these guys are going to attract each other. How much force? Well, the force can be described by this law. It's called Coulomb's law. The direction, you actually know the direction based on the charges. Again, like charges are going to repel, opposite charges are going to attract. So here I have opposite and here I have like. And what we can kind of say is we can say how much force is there, and we know that force is going to be in newtons, is related to some constant, and this constant is over here. It is a rather large number, and that's kind of important on the next slide. And we could even say that this constant k is going to be 9 times 10 to the ninth with these units right over here. This is going to be the charge of the first guy, so that's going to be charge 1, so Q1. This guy is going to be the charge of the other guy, so this would be Q2. And this would be the distance of separation squared between them. So there's my distance right here, and please don't forget to square it. A lot of times people do forget to square it. Again, the unit for charge is going to be a Coulomb, and it's always the unit that tells you what numbers we're talking about. This guy right here has got to be in meters. This guy right here has got to be in coulombs. This guy right here has got to be in coulombs. This is in some weird funky unit that makes everything work out. And the force, again, is going to be in newtons. This is actually going to look very similar to Newton's law of gravitation. So let's go ahead and talk about that guy really quickly. So if you think back to Physics 101, we talked about Newton's universal law of gravitation in Chapter 13, and this guy kind of looked like this, and it said if we have any two objects with mass, they're going to attract each other, and how much they're attracted by is going to be related to the mass of the first object, the mass of the second object, the distance of separation squared, and some universal gravitational constant, big G, which you probably don't remember, but I remember it very well, 6.67 times 10 to the negative 11th. And that was just some constant to make all the numbers work, and it had some units. If we come to Coulomb's law, it looks pretty similar. The force is going to be related to some constant. In this case, the constant is going to be a rather large number, 9 times 10 to the ninth. The charge of the first object, the charge of the second object, divided by the distance of separation squared. So these guys look very similar in that they both are inverse squared laws, or they divide by the distance squared, and they depend on some physical quantities, charge, mass, and there's a constant of proportionality. But in other ways, they're very different. Gravity could only be an attractive force, but this electrical force can be attractive or repulsive. Also, the electrical force, if we were to take a look at this constant right here, the constant of proportionality, 9 times 10 to the large, it's actually going to be a relatively strong force. The gravitational force is actually going to be a very weak force, and kind of one of the reasons for that has to do with this constant of proportionality. In general, the electrical force is much stronger than the gravitational force. And I just said in general, but I mean always. So let's just do a quick little calculation here. Just kind of do this off to the side. I didn't include a slide for you to put this on there, but suppose I had two charges, and charge 1 is going to have a charge of positive 2.5 microcoulombs, micro meaning times 10 to the minus 6. Charge number 2 being 5 microcoulombs, again times 10 to the negative 6, and these guys are separated by half a meter. Let's go ahead and calculate what force we're going to have on these two guys. So here we're going to have force is equal to k times q1 times q2 divided by that distance of separation squared. Again, this k value is going to be 9 times 10 to the ninth. charge number 1 is going to be 2.5 times 10 to the minus 6. Charge number 2 would be 5 times 10 to the minus 6. And the distance of separation is going to be 0.5. Again, please don't forget to square that. Very often I see that. And of course, on multiple choice, you're going to see that option. And this force of attraction would be 0.45 newtons. And you may be saying, well, that's not a lot of force, but that's not a whole lot of charge. The last question we need to ask, is this force attractive or repulsive? Well, these guys are both positive, and so it's going to be a repulsive force. Let's just get a little bit more practice using this. Suppose I had two particles, and I'll just make them positively charged particles just to make my life easier. What would happen if I place these same exact two particles twice as far apart? Well, we can immediately eliminate two of these guys. We can eliminate this one and this one because we know that they're further apart. The force should go down. And since the force is actually going to go like 1 divided by the distance squared, it's not just going to be half as strong. It's actually going to be 1/2 squared as strong, or 1/4 as strong. Now, some other implications of Coulomb's law is going to be that the distance matters, and I'm probably not telling you anything that I didn't already tell you. Objects that are closer are going to attract more. Objects that are further away are going to attract not as much, because force is going to be inversely proportional to the distance squared, and as the distance gets bigger, you're dividing by a bigger number, so the force has to go down. This actually leads us to something called charge polarization, which I'll talk about quite a bit more in the next couple of slides. But if you've ever gone ahead and taken a balloon and rubbed it onto your hair, then what might happen is this balloon is going to gain a whole bunch of electrons, probably from your hair. And if you were to take this thing, it's going to stick to a wall, and it would actually stick to a wall that is not charged. So any charged particle can actually attract an object that is going to be neutral or have no net charge. And kind of what's going on with that is here we have a bunch of negative charges, and that's going to repel all the negative charges of the wall. And if they are free to flow, then they will. If they're not free to flow, they're going to try to get as far away from these negative charges as they can. Then what would also happen is that would force the positive charges to become as close to these negative charges as they can, and distance is going to matter. These close positive charges are closer to the balloon than the negative charges, and so they win. There's going to be a net attraction between the balloon and the neutral wall because of this. We have a special name for this. What we actually call it polarization, and what we're doing is we're polarizing the wall. We're putting all the positives over here and all the negatives over there. Now, before I talk a little bit more about charge polarization, I want to talk about how electrons can actually move inside of neutral objects. And it turns out that what the object is made out of is going to make a difference. We're going to have objects that are called conductors, and objects that are called conductors have electrons that are pretty much free to move. There's lots of electrons in that outer shell. They can be jostled around pretty easily, and they can wander around in the material with relative ease. Something that is a good conductor of charge is also going to be a good conductor of heat. So think of any metal. Think about copper, or aluminum, or steel, or iron, or anything like that. An object that holds onto its electrons quite well is actually called an insulator, and they can move around a little bit, but not nearly as much as an insulator. And they're bound tightly to the nuclei, not lots of electrons in those outer orbits, and so they're not going to be free to wander like they are inside of conductors. And an object that is a good conductor of heat would also be, or a good insulator of heat would also be a good insulator of electricity. So think about things like rubber, or glass, or air, or wool, or wood, stuff like those. We also have things that are called semiconductors, and sometimes they can be an insulator, and sometimes they can be a conductor. Essentially, they're insulators when they're pure, they're conductors when they have impurities. Kind of an example of a semiconductor would be a solar panel. And a solar panel, when it's exposed to light, it's going to be able to produce charge, and that's going to be just an example of a semiconductor device. We're also going to have things that are superconductors, and these superconductors essentially have zero resistance, and that's kind of a fancy way to say that pretty much most, if not all, of the electrons are free to flow wherever they want, and electrons are going to flow indefinitely once we get a current flowing. There's going to be nothing to impede the flow of these electrons, and so very little resistance is going to happen, and this object is not going to heat up. Examples of these might be what we would see on like a maglev train or something like that.